So for the second half of these notes, let's move to the back page and let's look at what happens or how we can calculate molecular speed based on the mass of the particle. Now, we sometimes refer to the speed of gas molecules as the root mean square speed, or for short, RMS speed. And to determine the speed, we use this equation that the RMS speed or RMS velocity is equal to the square root of 3 times the gas law constant times temperature divided by the molecular weight. Now, a couple of really important things. Now, of course, this is gas law, so you know that it has to be in kelvins, but this is the one that messes people up every single time, and that's molar mass. Look at what molar mass has to be in. It must be in kilograms per mole. So when you look up that 16 grams per mole, it's actually 0.016 kilograms per mole. You have to change the mass to kilograms. Also, look at R. We've been used to using 0.0821 liter atmospheres per mole Kelvin. Well, we're going to use a different one this time, and it has to do with how we're going to be able to cancel the units. In this case, we're going to have to use Ladamolk's cousin, Joule Molk, and it's 8.3145 joules per mole Kelvin. We've simply converted the liter atmospheres to joules. We've used a conversion factor to do that before in a previous unit. But we need it to be in joules per mole Kelvin in order to get kilograms to cancel and us to be left with a speed. Now, another thing, the reason we need that is because we've got to remember that what a joule is. A joule is a kilogram meter squared per second squared. That's a joule. So in order to get joules to cancel in this equation, we're going to have molar mass in kilograms. And we also, the part of that we don't want to cancel. We want to be left with meters squared per second squared, because once we take the square root of that, we'll end up with meters per second, which is a velocity or speed value, so unit. So that's why we need to use those specific units for molar mass and for the gas law constant. So let's look at this. It says calculate the RMS speed of nitrogen molecules at 80 degrees Celsius. We really only need to know the temperature, and we can calculate the RMS speed. Watch it. AP's liable to do this to you. Nitrogen is diatomic, so when you come up with its molar mass, you better be remembering that the molar mass of free nitrogen is going to be 2 times the 14.01 that you look up on the periodic table. So keep that in mind. Also, remind yourself that 80 degrees is going to be, you're going to have to add 273 to that. So you're going to end up with 353 kelvins for your temperature when we do this calculation. So the RMS speed then is the square root of 3RT over M. Remember that we need R to be the 8.3145 kilogram meter squared per second squared per Kelvin mole. So it's joules per, it's joule molk, joules per Kelvin mole. So that's going to be your value for R. And the temperature we just established, I'm going to keep extending my square root out, 353 kelvins. And then we're going to divide that by the molar mass. Now remember, the molar mass of nitrogen, we would normally think of the molar mass as being 14.01 times 2, which is 28.02 grams per mole. It cannot be in grams per mole, guys. It must be converted to kilograms per mole. So 0.02802 kilograms per mole is what I'm going to need to put into that calculation. So please don't forget to do that. One of the most missed things that happens on the test. So when I get rid of these units and start canceling, I should notice that my kelvins cancel, my moles cancel, my kilograms cancel, and I'm left with meters per second squared, which is exactly what I wanted because I want the square root of that to end up with units of meters per second. When I multiply and divide this out then, I end up with the and take the square root of that, I end up with the RMS speed being 561 meters per second. So that's the RMS speed equation. And finally, the last example on these notes deals with Graham's law of diffusion. Now, Graham's law of diffusion, a fusion is the passage of a gas through a tiny orifice into an evacuated chamber. The rate of a fusion for two different gases, you can compare it using this equation. Now, think about it also. It's going to be it's going to be an inverse relationship. The bigger the mass of the gas, the lower its rate of diffusion is going to be, and vice versa. So look at how this turns up on the equation. The rate of diffusion of gas 1 divided by the rate of diffusion of gas 2 is equal to the square root of the molar mass of gas 2 on top over gas 1 on bottom. So keep that in mind. Now, most of the time, I'm going to write the equation like this. Rate 1 over rate 2 equals the square root of molar mass 2 over molar mass 1. It doesn't matter which is which. I tend to try to put the unknown on top, simply because it makes it easier to solve algebraically. It doesn't really matter. Just make sure you pay attention to how you're going to solve this. So it says we have a pure sample of methane, and it's found to have fused through a porous barrier in 1.5 minutes. Under the same condition, an equal number of molecules, now this is going to become really important to us, of an unknown gas that fuses through the barrier in 4.73 minutes. What's the molar mass of the unknown gas? Okay, so I want the unknown gas, the molar mass of the unknown gas to be M2. So I want rate 1 over rate 2. I want the first example to be my known CH4, R1, and my unknown to be R2. We got to be careful. The first thing we want to do is just to slap 1.5 over 4.73 into this equation, because once again, R1 over R2 is going to be equal to the square root of M2, molar mass 2, over molar mass 1. But those are not rate values. Those are minute time values. Time and rate are not the same thing. I need some number of particles or some number of moles per a time value in order for it to be a rate value. That's where this equal number of molecules comes in very, very handy, because this equal number of molecules, let's call it N. Is for, like, we could call it X, we could call it whatever we wanted to, but let's call it N for the number of molecules. Now what that means is that the rate is going to be N, the number of molecules per time. So would you agree that the rate of CH4 is going to be N over 1.50 minutes, and the rate of the unknown gas is going to be N over 4.73 minutes? So we're going to be able to put that into the equation. And let's look at how that plays out. We're going to have, I'm going to raise this up a little bit so that we can have a little more room to work. I'm going to have N over 1.50 minutes divided by N over 4.73 minutes is equal to the square root of the molar mass of M2, which is what I'm looking for, over the molar mass of the first substance, which is CH4, which is going to be 16.05 if you add up its molar mass. And it doesn't matter if it's grams per mole or kilograms per mole, because those units we'll end up with those units in the end anyway, so we can always convert them at the end. Now, solving for this, be very careful. Yes, the n is going to end up canceling, but what we end up with when it cancels or reduces to 1 is 1 over 1.5 over 1 over 4.73. The big mistake is to say that that is the same thing as 1.50 over 4.73. It is not. Think about why. Let's go over here and let's just do this side calculation real quick. If we've got 1 over 1.5 divided by 1 over 4.73, think about what happens. We would actually be taking 1 over 1.5 times the reciprocal, 4.73 over 1. So look at what we end up with for our next term. We end up with 4.73 over 1.50. Be very careful, you'll end up with a reciprocal there and you'll get the wrong answer. So 4.73 over 1.50 is equal to the square root of m2 over 16.05. So a little more room to work with here. This ends up being 3.153 when we divide it is equal to the square root of m2 over 16.05. And what I'm going to do now is simply square both of these to get rid of the square root. So by squaring this, I end up with 9.9435. And remember, squaring a square root simply gets rid of that whole thing. We end up with m2 over 16.05. And all I'm going to do now is simply multiply both sides by 16.05. And I end up with m2 equal to 160 point, if I want 3 sig figs, grams per mole. That's a little more difficult of a problem than we normally face with Graham's law of diffusion, but I wanted to give you the most difficult type where you actually had to come up with this n value for the same number of moles. Usually it's easier than that, and we just have a straight rate for both of those values, so it's easier to solve. But that will, again, let you see a more difficult problem in the notes instead of facing it later in the worksheet.